Okay, thanks for coming. It's great. This is the graveyard slot, so it's nice to see a good crowd here. So my name is Jim, and I'm going to talk a bit about a new Hadoop distribution that we've been working on called Hops and how we use Flink in it. I'll start out by talking a bit about how I see Flink fitting into the larger picture of big data, for want of better terms. So many of you will know this is Pep Guardiola. He's probably the world's most famous football trainer, and he speaks 5 languages fluently. He's a polyglot, right? And some say that makes him a better football trainer because he can speak to the players in their own native language and he can motivate them that little bit better. Now, if we think about big data, we've now entered the era of polyglot data parallel processing. So you may have heard the term polyglot persistence in databases. We're there now in terms of data parallel programming. So if you're doing stream processing at this conference, everyone will say, go for Flink. If you're interested in deep learning, people will say, go for TensorFlow. If you're interested in doing maybe pipelines and batch, Spark, MapReduce, you can have your debates. SQL and Hadoop, you can go for Presto, Spark SQL. And then machine learning, probably Spark. Don't mean to offend anyone here. But the point is that there's different tools which are suitable for different jobs. And unless you're Jeff Dean, you're not going to know all the tools, potentially. But what we've seen at this conference quite a lot is that companies are polyglot by nature. So if you're a large company, we've seen some very large companies here. We've seen Uber, we've seen Alibaba, and so on. And they have huge deployments, right? So these huge deployments, they can dedicate some servers, dedicate some people. They can run Flink standalone. That's no problem. What about the rest of us, the little guys? So for the rest of us, the little guys, we need to try and get this into the context of our data processing platforms. Maybe we have a few racks. Maybe we have some time on Amazon or Google Compute. We need to think about how are we going to solve a given problem with a given tool, and we like it all to kind of work together. So Flink doesn't exist in isolation. Flink standalone is not the only tool that's out there. You need to think about, from your data processing layer down, what else am I going to do? What metadata services am I going to use? Do I need to use Hive? Do I need to use some access control system? Maybe Ranger, maybe Sentry, or maybe Hopsworks that we'll talk about today. And then when you come down to your storage layer, you might be running HDFS, like a lot of people we saw. I think that King were running Ceph, I think, was it? There's some Flink people here. But so there's still some diversity in terms of storage. If you're running on Azure, you might run Windows Azure storage. You may even run MapOR. Now, finally, at the resource management layer, you can take your pick. If you want, you can run Yarn, you can run Mesos, or you can run Kubernetes. And each has their different strengths. So I'm going to talk a bit more about the traditional Hadoop stack today, because I'm going to talk a bit about our Hadoop distribution as well. And this includes Yarn, HDFS, and we have a bunch of metadata services that some of them will come across today. OK, so this is Flink for the little guy, right? So Flink for the person who wants to have a platform to do polyglot data parallel processing, not maybe be stuck with just Spark or just Flink. You can use the best tool at hand. So what I'm going to talk a bit about is a new distribution called Hops Hadoop. It's fully UI-driven. It's pretty easy to install, we think. And I'm going to introduce a new concept that Hops Hadoop provides that's not available in other distributions called project-based multi-tenancy. So that differs from the multi-tenancy you hear at a conference like this, which is I'm running a long-running streaming job and some maybe short-term batch jobs on the same hardware. Sure, that's multi-tenancy, but it's not multi-tenancy from the perspective of users. That means if you think about a database, how do I have multiple users use the same database but be protected from one another? How do I have multiple users on the same operating system and have different home folders where they can not maybe access the files in someone else's home folder? So that's the classic model of multi-tenancy I'm going to talk about today. OK, so this, just to put this in perspective, we're already providing this as a service. So Flink-as-a-Service is available as of today in Sweden. We have a data center up in northern Sweden in Luleå beside Facebook's data center. And we're running on about 54 machines right now. It's about 10 terabytes of memory. And I don't know how many cores it's that, probably 1,000 cores or something like that. We've about 100 users. And Flink is one of the services provided. So you've got Spark as a service, Flink as a service, and a lot of people like storage, just they want to store a lot of data. I'm a climate scientist, I'm bioinformatician, give me free storage. That sounds good. Okay, so what is Hops Hadoop? So Hops Hadoop is, it started out as a file system, the project. We're interested we're a research organization, so we straddle both KTH, which is a university in Stockholm, and SIX, which is a research lab in Stockholm. And both groups have contributed to the development of this platform. But the file system itself is a way to scale out. To begin with, it was a model to scale out HDFS. So if you're familiar with HDFS at all, you'll be familiar with the fact that there's a name node that stores metadata. So that means the path components in files and what blocks do they map to, where are those blocks stored on the data nodes down here. So in traditional Hadoop, you would have 1 or 2 nodes here and maybe thousands, up to 5,000 nodes down here, the data nodes. So you can pretty quickly infer that this is a bottleneck in the current HDFS architecture. So in the current HDFS architecture, you have a single active name node and a standby name node. So if the active name node fails, you can fail over to the standby name node. So what we've done is introduce multiple you can think of them as stateless name nodes. But we do have a leader, and we have a leader election protocol without Zookeeper. And these name nodes basically provide the name node as a service. So if one of them fails, another one will take over. And this allows us to scale out the cluster. So we can scale out the file system basically by either adding database nodes, because that's where the metadata is now stored. This database, by the way, NDB is the name for it. It's an open source, in-memory, distributed, replicated, new SQL database. And we'll see that it can handle many millions of operations per second. It's GPL v2 licensed, but we integrated it with the Apache code, so it's OK. So this is the file system. We also have done the same thing to Yarn. So we started out first with the file system, and then we moved on to Yarn. And what we saw in Yarn, if you're familiar with Yarn, Yarn has a resource manager. And the resource manager stores the state of the cluster. It stores, it knows about all of the containers that have been allocated on these nodes at the bottom called node managers. It knows which applications they've been allocated to. It knows how much free space there is, how much free memory, CPUs there are on these machines. And it makes scheduling decisions. So applications ask for resources, and the scheduler decides, OK, you get these containers on these machines. If you look at the internals of the resource manager in Yarn, in Apache Yarn, you'll see that it runs firstly on a single JVM. So again, it's a bottleneck for this system here. And you'll see also that it has lots of different components that you can actually break up. So there's a component called a resource tracker. And what the resource tracker does is handle the heartbeats from the node managers. So if you're in a large cluster, and we could take like a 5,000 node cluster being a pretty large cluster out there, there are some that big. What they do is that they'll set the heartbeat time, which is by default 1 second. They'll make it 3 seconds so that they can handle the load. And that load will make up the majority of the requests that are coming into the resource manager. So if you're using Yarn and you wonder why does it take a long time for an application to start up, and you say to people, well, there's a JVM startup time, or if you're using Docker containers, there's a Docker container startup time. Well, in fact, a large part of the delay is these heartbeats, because if you're heartbeating every 3 seconds, what will happen is you'll send a request maybe to start your application. It will start an application master. Then you'll wait 3 seconds for the heartbeat to get handled to send a response back. And the same thing will happen when you allocate the containers. You wait 3 seconds for the response to get back. So you can see there's quite a lot of delay going on there. If you can reduce the time of these heartbeats, you can improve the interactivity of Yarn. So that's what we're doing here, because we're making these are basically now stateless servers. Our cluster state's no longer on the JVM, it's in the database again. And then we have a single scheduler that handles all the application master requests. So this thing scales out quite well. So I don't have any figures today on this, but 10K node clusters work quite well on this. So this is the file system. Just to show you, these are very recent figures. We've been working with Oracle and Spotify on this, and in particular Oracle during the summer. So you can see here we have on the x-axis the number of name nodes, and on the y-axis we have the number of operations per second. And this particular benchmark is based on Spotify's workload. So this is the set of applications used at Spotify. What operations do they perform on the name nodes? And you can see here that from about 3 of our name nodes, we outperform their name node, and we scale linearly at least up to 30 odd nodes. And we'll probably go higher. So you can see there's a nice milestone up there for us to reach in the near future. So this is on an 8-node database. So we can scale the database out to 16. It'll go all the way up to 48 nodes. So we don't know if we'll get that much hardware. Getting that much hardware is actually an issue. Okay. So if the name nodes can handle a huge amount of throughput, can we have bigger clusters? And the answer is yes, because we have more memory. So in the Apache HDFS version, the metadata is stored in the heap of a JVM. And there's a practical limit of around 200 gigabytes. After that, garbage collection causes large pauses. So you're kind of maxed out at a few 100 million files. Spotify have about 300 million files in their cluster. It's a 2,000 node cluster, 90 petabytes. But we can easily go up to 12 terabytes. So that means billions of files, the order of billions of files. Okay, so that's the Hadoop distribution that we're running on. What makes it interesting from my perspective is not the scalability, right? The scalability thing is great, and people say, yeah, sounds kind of cool. But what happens if the cluster state for Yarn is external? It's in a database. What happens if your name node state is now in a database? Databases can be integrated with different things. You can export the data from them easily. You can hook up and stream for any changes that are made to the namespace. So we do a lot of different things with the data now that it's in the database. And we based a front end around that. It's called Hopsworks. So the first thing we came up with was this notion of project-based multi-tenancy. And it kind of came from thinking about hierarchical file systems. So if you read the kind of the blogosphere as it currently stands in Hacker News, you will think that object stores are the future. We have to go to object stores. Hierarchical file systems are dead. Let's move on from there. The thing about hierarchical file systems is they give you lots of nice properties. So you can have a directory, let's call it your home directory, and you can shield it or isolate it from all the other users in the system. And that way you can have a multi-tenant file system quite easily with using the property of hierarchy in your file system. So everything in your subtree belongs to your project. So if this is HDFS here and we create a project, we get a subtree in the file system. And that belongs to your project. So if someone's running in another project, they're in another subtree in HDFS, well, they can't access your files unless you explicitly authorize it. And the way we do this is, what we're actually doing is we're creating a new user identity per project. And what we're doing is we're exploiting the fact that the data is in the database. So this is to think about it this way. If you're in Hadoop, you have one identity. You've got a Kerberos identity. In our system, you have an identity to log in with. But when you go into a project, you take on one identity, the project-specific identity. And that identity is a table called users. And it has a foreign key. And we can have foreign keys from this table to the actual folder here in HDFS. So if you remove the folder, all the users disappear. So if we go into the file system and remove the project, all the metadata associated with the project just magically disappears. We don't have to write lots and lots of code to handle any situations you would have if you had external servers and you need to then ensure the consistency of your metadata. And you would be writing distributed protocols to do that. Eventually consistent distributed protocols. It will be hard. That's what Cloudera and Hortonworks are doing now today. So we have this project abstraction, and the project consists of, as I said, a subtree in HDFS, but also consists of a number of users. And your users can be an owner of the project, or they can be a data scientist within it. So we have those two roles. So owners can upload, download data, but data scientists can just run programs. You have a number of topics in your project. We have notebooks in it, and then we have quotas. So you have so much storage in your project, but also in Yarn, we can say you only get 1,000 CPU hours. And we can do it again because the data is in the database. So every time a container is allocated or deallocated, we listen on the change log for the database, and then we just log those events and say, okay, let's update the quota for that project. It ran a container for the last hour, and we'll decrement that. And even cooler than that, if you have at Spotify, they have this issue where there's no incentive for users not to spin up big Spark clusters. Right? They're running Yarn. You run up the Spark cluster. It takes 20 minutes to get it up. You go out for lunch. You come back after lunch. It's ready. Nice. But it wasn't used for 40 minutes while you're at the rest of your lunch. So there's no incentive model currently for Elastic Hadoop. Elastic Hadoop, we don't have it. You need to have a pricing model to have elasticity. So what we can do here is we can basically say that you get 1,000 CPU hours, but the price will change based on the load of the cluster. So if the load is high, the price is high. But if the load is low, the price is low. So we want to incentivize people to be good citizens in Yarn. And this is already the case in Google. So Google Borg already does this internally with their squads. And finally, it's one thing to be able to isolate different projects from one another, but you might want to have data that's shared between projects. So we have this notion of sharing data sets or topics in Kafka across projects securely. So you can authorize another project and say, okay, you can have this data set, you can have read access to it, or you can have read-write access to it. And the same for Kafka topics. Okay, so that's the project-based multi-tenancy model. How do we implement it technically, if you're interested? So I said before we have a UI for everything, so we're not giving people command-line access right now. Technically we could do it, but we're not really interested in doing it right now. So what you do as a user, you authenticate with a web application server, and you maybe have some projects. So here we have a user called Alice, and Alice is a member of the project called Users, not a very good name, and another project called NSA. So when Alice authenticates and navigates to the user's project, Alice will be active within that project. So when Alice does something in the file system, or does something in Yarn, or does something with Kafka, that will be the username that's used. Right, so if Alice is a member of the NSA project and she's active in there, you'll see that that will be the username used in the file system. So if Alice has access to some files here in the project users, the other Alice, the NSA Alice, doesn't have access to those files. Right, so you can trust Alice in the NSA project and say, okay, you can run all the jobs that you want there. I'm not worried about you copying data from here to over here, or cross-linking data from this project to this project. So that's a big problem currently, and you can't do this with Kerberos. With Kerberos, you have one identity, and that's it. Right, so you need dynamic roles to do this, and dynamic roles are expensive, but we do it in the file system by creating new users. So dynamic roles have no performance overhead for us. So it's quite an important point. Okay, so how we do it, technically, if you're interested, we use secure impersonation. So our web application service, Hopsworks, can launch the jobs as the given user. And for Kafka, we don't have secure impersonation, so we use certificates. So we generate a certificate per user. So Alice will have different certificates for each of these projects she's in. Okay, so I mentioned we don't have Kerberos, so we're not supporting Kerberos right now today. I can't say we won't in future, but right now what we're doing is, for each project, a user will get allocated a new X509 certificate. So that is the project name and your username mangled together. We write that into the certificate. So if you read the certificate, you can extract that username from the certificate. The services like Kafka, for example, they're also given certificates, and both of the user certificates and the services, they're signed by the same CA. So when services start up, we have an agent on the nodes, and they send a certificate signing request to Hopsworks, which signs it and then returns back. So a service like Kafka, what it'll do is when it gets a request from a client, and it's using SSL and it's using certificates, Kafka gives you a hook, actually, in fact, a class you can override. And in there, we can just extract the user ID from the certificate. And we can use that to identify the caller. And that's basically the principle of Kerberos. Kerberos key tabs identify the user securely. And they'll identify services and hosts and things like that as well. But we can use SSL certificates for the same effect, I guess. So Netflix do this if you're interested in reading up more this kind of model. There's a system called Bless. Their certificates are very short-lived, but it's the same basic principle. Okay, so when you're in technically, if you're interested in how it's working behind the scenes, when Alice authenticates and maybe she adds someone to a project or removes someone from a project, we have to insert or remove certs, and we store them in the database, the same database that the metadata for the file system and for Yarn is stored in. These, again, need to be signed by the root CA, as do the services. Okay, so Flink. So we're running Flink. Flink-as-a-Service on Hopsworks. Flink, in our case, is running on Yarn. All the services are running on Yarn. Now, if you were at Stefan's talk yesterday, where he talked about the future of the cluster managers in Flink, you'll see that it's an area under a lot of change right now. So one thing we wanted to do, for example, was run Beam on top of this, but we're running in detached mode currently, and Flink supports detached or blocking mode, and we can't run in blocking mode. And it's technically, it's because The Flink client is launching these jobs into Yarn, and the Flink client is quite a heavyweight client. So it includes Netty libraries, and they conflict with our existing Netty libraries, and there's a bunch of other libraries in there. So we need to kind of, to make, I guess, to support Beam and things like that, we need the client to become like a REST client or something like that, which would be ideal. And that fits into our existing kind of microservices model. You know, we're using services like Kafka, Dr. Elephant, Uzi, and things like that as REST-based services from within the web application. Okay, so we're running Flink, we're running it on Yarn, we're running it in detached mode. And the way that it works is that basically when the client starts your Flink job, the Flink client has to run locally, and then it'll exit after the job has been submitted to Yarn successfully. That means we can't get back accumulator results from our web application. We can only say there's a Yarn job running, we can kill it. It's kind of a bit messy. It makes it more difficult to clean up your applications if you had to handle a kill message from Yarn. But there's a lot happening. Like there's this new dispatcher in the works which will resolve a lot of those issues for us. So what's interesting about our support for Flink and also Kafka, because the two of them come together like peas in a pod, right, is that we've made it much easier to write these applications in our architecture. You may think this sounds very complex, everything sounds very, very difficult, but when you have a framework, you can simplify a lot of things on behalf of users, right? So we have an abstraction of a project. We know you're running within the context of the project. We know what topics are in the project. There's a lot of things we can do. So if we look at how a job is submitted in Hopsworks currently to Yarn for Flink, the user will say, I want to launch the Flink job. What's going to happen first is that the web application will go to our database, get the certificates for that user. Then we'll get the endpoints for all the services, so the Kafka broker. If you're using, also we'll see that there's a registry for schemas in Kafka here on Hopsworks, and any other endpoints that you need in your application. And then it launches the job on some containers out in Yarn. But it's also passing in configuration information as well as parameters. The certificates, if you're familiar with how Kafka security works, it's available since 0.9. You have your Kafka config file that you have to set up, but it has a hard dependency right now that the certificate is stored in the local file system. So you can't pass it in as an input stream or anything. So what we have to do is we have to get those certificates from here and put them out here on all the nodes, right? So that's an operations kind of nightmare area. You would not want to do this in normal case. And this is where Yarn comes to our aid here. So what we do is when we launch our job, you have the ability to include what are called local resources in Yarn's jobs. And they can be private. So we're materializing these certificates as private local resources on the local file system where the containers are actually launched. And the nice thing about that is that when the container exits, Yarn will clean them up for us. We don't need to worry about all that on our part. Also, we don't need to necessarily, our application doesn't need to read them. It doesn't need to know where they're stored on the local file system. We can provide a nice utility which will do it for us. Similarly, our utility can also get the schema from our schema registry for us. And finally, your application just has to worry about then consuming and producing from Kafka. So I'll just show you this in a bit of code, because most people prefer code. This is a very skeletal version of a Flink stream producer with secure Kafka. Maybe if you're running in standalone mode, what you would end up doing is you get your streaming environment, you get the topic, maybe it's supplied by the user. You then need to discover where is the schema registry, where are the Kafka broker endpoints. I need to create my Kafka properties file with the cert details, create a producer. I need to get my certificates somehow onto the hosts that are running it for your user. I need to download the schema for the topic from my schema registry. And I need to do all this securely, right? And finally, when I've done it, then I can get my data stream and I can write as a producer to Kafka. Now, the thing is that this is kind of mixed a lot of this, right? It's not just developer-specific things. You might think, well, there's some ops stuff there as well, right? How do I get certificates out securely and so on? So this is not a trivial thing to do. So how do we do all of this? Well, we do it in one line. So that's it, right? That one line will do all that for you. So the Kafka util is a utility we've written. It's up in GitHub. And you can use it just to get back your producer. And with your producer, you can then write to it. So it makes the code much nicer and cleaner for application developers. It's the same for consumers. You just call Kafka util get Flink consumer, and we do the same, something similar for Spark, if you're interested. Okay, I'm going to talk a bit about Zeppelin. Zeppelin we support as a notebook on Flink. Flink streaming doesn't really work on it, so we haven't found that there's a lot of users showing it. I know there was a talk here this week on Kafka, sorry, on Zeppelin Flink. We also support, I mentioned already that we support easy installation of our platform and also Flink. We have a tool called Caramel, which is an orchestrator for Chef. And it really is just point and click to install the entire platform. So I have time to do a demo. I was fighting with some problems with the resolution earlier on, so we'll see what happens when I press escape. Hopefully things will go okay. But what I'll try and do is I'll show you basically how to go from the very start. You have nothing, you want to get this, you think this sounds interesting, relatively interesting. How the hell do I, reproduce what this guy's just been talking about? Well, what we do is I've just pressed the button for Caramel. It's going to load Caramel here. Hopefully we'll see it in a second, if the internet's still working. Is the internet working? There we go. So this is the front end for Caramel. In Caramel, a cluster is just a single file. I'm going to find one in here. Oops. I have no mouse on the screen, so I'm kind of going blind here. There we go. So this particular one here is if you download Caramel from the website, you'll see that there's a bunch of sample clusters in there. Some Flink, there's one which is Flink versus Spark streaming if you're interested. You can run it. It's going to run just Apache Hadoop. But anyway, so what Caramel does is it takes a definition of a cluster. It's just written in YAML. You have the services you want to install, how many instances of hosts you want to have on different machines. And it then runs Chef recipes to install everything. So it's quite slow. We will probably produce AMIs, which speed it up, which pre-install the software. But as of today, it's actually downloading all the software from my machine in Stockholm, which is about 1 gigabyte of traffic for install. We have good bandwidth in Sweden. It's fine. The really cool thing about it is that you can parameterize the entire cluster. So if I click on something like Apache Hadoop here, you can see that if I go through it, nearly every single configuration parameter you can overwrite in here. So for this particular instance, I think these are Amazon 3x. You can change the size of the amount of memory you want to give to your node managers, and so on. So I'll just launch it just to show you how it works. You can see that it's caching my secret access key. It's in a directory with only read privileges for the owner. If you're not comfortable with that, you can turn it off. I like it personally, and you can generate SSH keys if you don't have one. The nicest feature of it, I think, is that when you've created the cluster, you can just SSH directly into the machine. You don't need to download Amazon keys, because what it's doing is it's going to copy your public key into the authorized keys file of the machines that are created. So this developer machine you're using here, you can you work directly. So that's how you launch this platform. It's going to take a while, so it's not going to be ready by the end of the talk even. So I'm just going to show you Hopsworks running already. And this is running on VirtualBox. If you want to just run on VirtualBox, maybe you don't have an Amazon account, it's one line. You clone the Hopsworks Chef repository, and then you call run vagrant. You need to have about 12 gigs, though, currently. So I just logged in. This is the home screen. You can see that we have projects over here on the right-hand side. And what I'm going to do is I'm going to create a project. If the internet's still working, let's see. Here we go. So we create this project called FF Producer, Flink Forward Producer. So it's going to be a producer for Kafka. And I'm not going to talk too much about it, but you can search Elasticsearch for the whole website, and we've got some tours and stuff there. But I'm going inside the project now. So this is my project. You can see we have a number of microservices on the left-hand side. Zeppelin, we have jobs, job history, and Kafka. I'm going to just go directly to Kafka. And because I need to work fast, I'm going to go to the schemas. Let me just see if I can find okay. I think I need to just copy it out. It'll take 1 second here. Okay, so if you're familiar with Kafka, you'll know that Kafka supports Avro schemas. Confluent have a support for Avro schemas. Let me see. So I'm just going to create a schema for this a general schema. We'll call it my schema. We paste it in. We can validate schema, and then we can create it. Okay, so we now have a schema in our schema registry. I'm going to create a topic, and I'm going to use that schema. I'm going to call it my topic. Not a particularly great name. We have 2 partitions, 1 replica, and you can change those, of course. And let's go ahead. So now we've just created a topic. That was pretty quick. If you're interested in looking at more details, like the partition details, and if you want to do very fine-grained access control, you can do it. But what I'm going to do now is I'm going to jump over to a different user. So imagine we have a different user on the system. Did I log in as this user already? Oh, I did. I'm going to log out, sorry. I'm going to log in as someone else. I'll log in as myself. I have multiple email addresses, so it's not that one. Okay, so this is me up there. Doesn't look much like me. You can see I have no projects, right? So the other user who's out here, if I go back to the home page, has 2 projects, but I have none. So I'm going to create a project. We'll call it FF Consumer. And that's my project. And I can go into my project. And we can see that I have no Kafka topics, for example. So what I want to do is run a Kafka producer in the producer project, and I want to have a consumer consume from the same topic in the consumer project. The problem is the consumer doesn't have access to this topic, so I'm just going to share the topic with that project. And it's very simple. Okay. So now if we go back here, and if we, I guess if we just refresh, we can see our topic is here. Right? So the topic's available. What I need to do now is I need to run my job. So to run my job, I need to upload some data. I need to upload my jar file. This jar file you can build yourself from. I need just to zoom out a little bit. I'll just delete that one there. That's just a README. Sorry if the resolution's a bit low. I can't do much about that here. Okay, so I'm going to upload Kafka, this one. Sorry. I'll upload a new README as well. Okay. Okay, so I just uploaded them. This is running in Sweden. You can see it's actually really fast. Right? That's one thing you'll notice. So if I look at the new resources set, we can see it here. It actually shows animated GIFs. I know it's not moving there a little bit. The screen has gone a bit slow. But you can have nice interactive information about your data sets here. Right, so I'm going to now launch the Flink job. We get out of that. And we go to this jobs section here. And let's just get a producer up and going. We have Flink here. I don't know, can you see that down there at the back? I'll make it a bit bigger. So I need to pick my jar file that I just uploaded. I uploaded into the resources dataset. We can see that it picked out the main class because when we built it, we had a we'd set in the manifest we'd set the main class already, and I'm just going to run the producer. So this particular job just takes the name of the topic as a parameter, and also whether it's going to run as a producer or a consumer. The next set is all the yarn information, how much containers I want, and how much memory and cores I should get. I'll just jump over that, and finally, I'm going to run the job. So when I want to run the job, it asks me, here's the current price. It's 1x. Will I run it? I go, fine, let's run it. OK, so we have a producer now. It's running. You can see its state is initializing. It's a little bit slow. It's yarn. It's going to take 20 seconds to kick off. So I'm going to jump over here and create the consumer job. How are we going? All right. Oh, I forgot to upload the data set, didn't I? So I need to upload, sorry, the jar file here. OK, let's do that. If you have any questions, just shout out. Anything's not obvious. OK, so I just uploaded the jar file. It's not very big, you can see, because the dependencies are actually already in yarn. Right, so it's going to be a Flink job. I'm going to pick it out here. There we go. The arguments are pretty similar to the producer, except that we want to talk. We're going to write the output to HDFS, so I just have that included in the arguments, and then the format for the files that we're going to write will be there as well. So again, it's the same as before. I'm going to pick it as a streaming job. If that worked. And we create that. Okay, and then finally I can run it. So when I run it, you can see the price has gone up a bit because the cluster is a bit more loaded. Okay, so let's switch back and see how our producer is going. Okay, the producer is running fine. There is a job UI. We have some difficulties with Flink's UI, but Spark one works wonderfully. So I'm not going to show that right now because it doesn't look great. But what we can see here is, okay, so our consumer is now running. If you're interested, you can pop over to Yarn and have a look and see what's happening there. We don't give this view to the users, but like if you're an administrator, you might want to look at it. So what's interesting is you can see the user that launched it is our project name, and then the username, and then we have the other producer was launched by a different user in a different project. And where was our consumer? This is our consumer. So the consumer should have been writing to the resources folder, and we can see it has. Okay, so we've a couple of files have been written out here. Pending looks like we can have a look at it. And there we go. So we can see that we've been writing out to HDFS, and then we can preview the top of the file in HDFS, and that was that. So that's basically how the scenario I was talking about. We went through it. And I can show you, just out of curiosity, I think I have a minute left, Spark. So we did something similar for Spark. This is not a Spark streaming job, it's just a Spark job running with Kafka. Did I define it? Nope. So what you can see, it's slightly different with Spark. I'll just run through the Spark example just to give you a feel for it. What's different with Spark, which makes it kind of nice in some ways, is that it's the Hops Kafka, yeah, that one. Okay, is that we can store the history of jobs in our database, and if we want to, we can look up existing jobs, and then see if we find similar jobs. If we find similar jobs that match, we can say, oh, this is a similar job. Maybe you can take the same parameters. It worked out fine. So it's this pre-configuration phase. I'll just skip over it for now. And then you have dynamic executors in Spark, which is very nice. So it can scale to handle larger numbers of nodes if you need to. What I'm also doing here is you can see that I'm adding as a dependency this util, this Kafka util library that we have. So it's going to launch with the actual job. So the load's even higher in the cluster, so the price can up even more. So what's interesting with Spark is that Spark is a history server. Right, so the Spark history server will store the results of your job afterwards. Let's go back to the job actually because it's running. We can have a look at the UI. So the Spark history server, we integrate with a system called Dr. Elephant. You may not have heard of it. LinkedIn developed it. It's really fabulous. It gives you debugging information for your jobs, tells you how they went, and for users, a user can quickly find out, oh, this job ran out of memory because the driver did reduce by key and took too many keys in, and then it crashed. So because they have that data, then they know how to fix their job. So this particular job runs for a couple more seconds and writes the output to HDFS. So I think it says finished. The last thing you need to do is do log aggregation. So Yarn does log aggregation. It's a weak point in streaming because you don't want to aggregate your logs at the end. You want to get the logs as the streaming job's running, but we don't have that possibility currently with Yarn. So this was just writing out. We can see that we're reading from the same Flink topic that their producer was writing to. So that's that. And then the history server, it takes a little bit of time, but this is Dr. Elephant. You can see what happens is that I need to scroll over because the resolution's all over the place. What you can do is you can look at your job results, and it tells you with a bunch of heuristics. And here's the heuristics that Dr. Elephant provides you with. You can say, okay, didn't seem to be any problems with anything I wrote, but if there was, I would get them there. If there were problems with my configuration, I'd find out some of them there as well. Okay, so that's the demo over. I think I'm out of time. So if it likes this. Okay, great. So that was a demo. So just to summarize what we talked about Hopsworks and support for Flink-as-a-Service in it. We support both streaming and batch jobs. I didn't show Flink batch jobs. There's Zeppelin notebooks. I didn't get a chance to show that, but we have Zeppelin notebooks working for Flink. And we can see that with this framework, we can simplify how we use Kafka, secure Kafka with Flink in this particular example. And Yarn is still ongoing work in the project. The project has been running for several years, maybe 4.5, 5 years. A lot of people have worked on it over a long period of time. We still have quite a number of people working on it now. It's an open source project. We're a research lab. We really would like people to contribute, and particularly if you're a researcher and you're interested in file systems or resource management, this is an open source project. A lot of the data is there. There's so many algorithms we'd love to do, but we don't have time or resources to do it. So come talk to me, and we can see if there's anything of interest to you there. And that's it. Thank you. Questions? Do we have time for questions?
Yeah, we have time for questions. So, any questions?
Okay.
Please wait for the microphone.
I'm going to.
Thank you for your talk. At the beginning of the talk, you talked about the heartbeats of the name node. And
the heartbeats for the resource manager in Yarn.
So who's taking now care of the heartbeats since you took it off?
In the name node. Yeah. So in the name node, we actually heartbeat to all the name nodes currently. We block, but if we do block reporting in the file system, which is another protocol where the data nodes tell the name nodes how many blocks they have, which blocks they have, and so on. We load balance them over the nodes. We introduce a new RPC where the data node will say to the leader, hey, who should I block report to? And then they block report to that.
So all the information of the lookup tables of the name node now is inside the database, right?
They're tables, yeah. So we have about
before
the file
they were lookup files inside the memory inside the name node.
Exactly.
And now they are a database that is remote from the name node itself.
Exactly, yes.
Isn't there a delay when the system is small?
Absolutely, yeah. And we've spent many years optimizing this, yes.
Okay.
So, like, I'll give you an example. The most common operation is reading a file. 67% of Spotify's operations are it's called get block locations. It's the RPC on name node. When we started out, it was 70 round trips to the database. We have it down now to 7 primary key, with an average path length of 7. We have it down to 7 primary key lookups and an index scan. And that index scan will be localized to one data node in the database. It's called partition pruned index scan. Those 7 primary key lookups, if we get a cache hit on them, they're one batch operation. So we're only 2 round trips to the database. We can get it down to relatively good. So per name node, we're getting 30K per second operations, whereas they're getting 75K on Spotify's workload. If we increase the write rate, doesn't affect us. Our write rate doesn't affect us, but for them, their 70K will go down drastically very quickly because they have a global lock on the entire file system namespace. Yeah,
but we still have one name node, right?
They have one, yeah.
Okay, so it's still centralized.
Yeah, but the global lock is the big problem. So imagine for every write, you have to block all the readers.
Yep.
Yeah. So if you any write rate above like 2%, Spotify's 2.7%, it just like falls off.
Okay, thank you.
Yeah. You just shout out. I'll repeat. Are you talking about jobs in Yarn now or Flink jobs? So the Flink framework handles that independent of us. So the question was, do we support handling checkpoints, save points in jobs like Flink? Yarn doesn't care about the jobs, right? So it's the application masters and the data parallel processing framework's responsibility for managing their own state. And that's why Flink, for example, uses RocksDB typically locally.
Yeah, right. But if I want to update, I find something, or I write a job and then there's a mistake in it.
Yeah.
And I want to update it.
Sure. So right now, it's going to launch a whole new.
I just stop it.
Yeah, I mean, right now we don't have the ability in Flink to dynamically expand and shrink, but that's work in progress, as you will have heard. Right. So you launch a new Yarn job. Yeah. So your old job's finished, and then the new one. New job manager, new task manager, so off you go.
Yeah. Okay.
Okay, any more questions?
I'm out of time.
Out of time.
Okay, thanks very much.
Okay.